Have you ever tried to place our planet on the Milky Way's map? Start small, a person, a city, a world. Then step out to the moon, the sun, and the quiet lane we occupy in a crowded spiral disk. Distances stretch fast. Light that circles Earth in a blink needs years to cross our neighborhood and tens of thousands to sweep the galaxy. We live in the Orion Arm, not at the center, not at the edge, just one address among hundreds of billions of stars. Tonight we'll measure where we sit, how big the Milky Way really is, and what small means when numbers get huge. If clear, steady exploration is your pace, a quick like and subscribe helps others find us. Settle in. Let's scale our place in the galaxy. How small are we inside the Milky Way? To answer, start close and move out step by step. A person fits in a room, a house fits on a street, a city lives on a continent. Earth is one planet circling one star. Our star, the Sun, sits in a wide, thin disk of hundreds of billions of stars. That disk is the Milky Way. From the ground it looks like a hazy band, but it is a galaxy, a large system of stars, gas, dust, and dark matter bound together by gravity. Our address inside that system is not the center and not the edge. We live in a smaller spiral feature, often called the Orion Arm, a lane of stars partway out in the disk. The Milky Way's disk is about 100,000 light-years across. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Using light-years helps because space is so large that normal units stop being useful. Even simple facts need time units to make sense. Light from the sun takes about 8 minutes to reach Earth. Light from many stars takes years to arrive. The numbers build fast. Our nearest star beyond the sun is Proxima Centauri, a small red star a little over 4 light-years away, about 40 trillion kilometers. If the sun were the size of a small marble, Proxima would be another marble thousands of kilometers away, with almost nothing in between. Space inside the galaxy is mostly empty. Stars are far apart, even where they look crowded. That emptiness is why we don't feel the galaxy's motion as a rush of air or a pull underfoot. The distances are huge and the motions are smooth. Still, the galaxy holds together. At the center is a dense region packed with stars, orbiting a supermassive black hole called Sagittarius A*, often written Skya A*. A black hole is an object with gravity so strong that not even light can escape once it gets too close. Skya A times weighs millions of times more than the Sunday. It is not a physical anchor like a hook in space, but its gravity, along with the mass of stars, gas, and dark matter in the central region, helps set the orbits of the inner galaxy. We are about 26,000 light-years from that center. Our sun orbits the galactic center once every roughly 230 million years. That full path is sometimes called a galactic year. During the last galactic year, Earth went from early reptiles to dinosaurs to mammals and then to humans who build tools and wonder about where they live. Our species has not completed one full lap around the galaxy during recorded history. All of human civilization has taken place during a small fraction of a single galactic orbit. Scale changes how we think. On Earth, we build to human size. Roads, rooms, trees, bridges. Our senses work well at that scale. In space, we need models to help. Imagine shrinking the Milky Way so it fits inside a dinner plate. At that scale, the entire solar system, out to the far edge where icy objects orbit, would be smaller than a speck of dust on the plate. Earth would be far too small to see. Even so, that speck holds every life and every memory anyone has had. The model is simple, but it shows why words like big and small become weak in astronomy. We lean on comparisons to hold the idea steady in our minds. The Milky Way is also not alone. Astronomers estimate that the observable universe contains on the order of 2 trillion galaxies. Some are small and irregular. Some are giant ellipticals like smooth light balls. Many, like ours, are spirals with arms that curve around a bright center. In that vast population, the Milky Way is fairly typical, large, star-forming, and structured. It contains on the order of 400 billion stars. Around many of those stars are planets, rocky worlds, gas giants, and icy bodies. We have detected thousands of exoplanets, and simple reasoning suggests there are far more we have not yet found. Being small inside a galaxy does not cut us off from it. The atoms in our bodies come from stars. Hydrogen, the simplest element, has been here since shortly after the universe began. Heavier elements like carbon, oxygen, nitrogen, calcium, and iron formed inside stars and in the violent ends of massive stars called supernovae. When those stars died, they spread these elements into space. Later, gravity gathered that material into new stars, planets, and, in at least one place, living cells. Saying we are made of star stuff is not poetry, it is chemistry. Even with that link, our minds struggle with distance and time together. When we look at the sky, we are looking into the past. Light takes time to travel, so the farther a star is, the older the picture we receive. A star 100 light-years away is seen as it was 100 years ago. The Milky Way's width is about 100,000 light-years, so light from one edge needs 100,000 years to reach the other. In a sense, any map we make of the galaxy includes different times mixed across space. The light reaching us now from distant parts left long before humans learned to farm or build cities. Motion adds another layer. Earth spins once per day and orbits the Sun once per year. The Sun and its planets move around the galaxy at a few hundred kilometers per second, roughly 200 kilometers per second in the local frame. That speed is fast enough to cross a large country in seconds, but the motion is smooth and the space between stars is empty, so we feel no wind or tilt. The stars seem fixed, yet they are not. Over long times, their positions change slowly as they follow their orbits. Our place can feel small to the point of vanishing. The galaxy is huge. Our planet is tiny by comparison. Still, something rare is happening here. Matter has arranged itself into thinking systems that can measure, compare, and ask questions. We do not make the stars turn or the galaxy hold together, but we can describe those motions and test those ideas. That ability is part of our place. It does not make us large, but it does make us connected. To keep the ideas clear, it helps to define a few terms simply and then move on. A galaxy is a large group of stars, gas, dust, and dark matter held by gravity. A spiral arm is a region in a spiral galaxy where stars and gas are denser, often forming a long, curved lane. A black hole is an object with such strong gravity that beyond a certain boundary, called the event horizon, light cannot escape. A light year is a distance equal to how far light travels in a year. These words are tools. Once we set them, we can describe the Milky Way with less strain. From inside the disk, our view is edge-on. That is why the Milky Way looks like a ribbon across the sky. In dark places, far from city lights, the ribbon is bright and detailed. You can see dark lanes, their name is dust lanes, where clouds of gas and dust block the light of background stars. Elsewhere, you can see patches and clusters where stars crowd together. To the eye alone, it appears soft. But a telescope shows countless points. Each point is a star, many with their own planets. The sun is ordinary as stars go. It is a yellow-white star of medium mass and age. Many stars in the galaxy are smaller and cooler, called red dwarfs. Some are larger and hotter. Some are old and faint, called white dwarfs. A few are massive and short-lived, burning bright and dying young. Around these stars, disks of gas and dust can flatten and clump to form planets. We know this now because we have seen disks around young stars, and we have measured dips in starlight when planets pass in front of their stars. The disk we live in is not perfectly flat or quiet. It warps slightly at the edges. Spiral arms are sites of starbirth, where gas clouds collapse under gravity. Supernovae carve bubbles in the gas. Magnetic fields thread through the disk. In the halo around the disk, old stars and faint clusters orbit along bigger, more tilted paths. Surrounding all of this is an even larger halo of dark matter, a form of matter that does not give off light, but shows its presence through gravity. Dark matter helps hold galaxies together. Without it, the stars we see would not be enough to keep the disks from flying apart at their measured speeds. When we ask how small we are, we also ask how to think about meaning at this scale. One way is to connect big and small through the same laws. Gravity shapes the paths of stars and holds you to the ground. The rules of atomic bonds build both living cells and interstellar molecules. Heat flows, light travels, and matter changes state in ways that repeat across scales. A neuron firing and a star orbiting are not the same, but both follow regular patterns we can test. We can also use models to bring the sizes down to something we can imagine. If the Milky Way were a city, the solar system would be a tiny apartment. If the sun were a grain of sand, Earth would be a much smaller speck nearby. The nearest star would be another grain of sand, far across a stadium. The galaxy would be a wide ring of sand around a whole region. These pictures are crude, but they help the mind keep hold of the large idea long enough to make sense of it. Another way is to use time as a scale bar. Set 1 second equal to 1 year. In that model, Earth's orbit takes 1 second. A human life might last a minute or two. A civilization could span a few minutes. A full orbit of the solar system around the galaxy would take several years at that pace. The galaxy has been in place for billions of years. In real time, in our fast clock, that is many tens of thousands of years. With that view, our moment is small, but not zero. It fits inside the story. Across the galaxy, different environments host different processes. In the spiral arms, gas clouds cool and collapse to form new stars. Some of these stars heat and carve their surroundings with radiation and wind. In older regions, stars age and shed their outer layers, returning material to space. In star clusters, gravity pulls many stars into a shared dance. Near the center, orbits are fast and crowded. Far out in the disk, they are slower and quiet. Yet the whole system still turns as a unit, a pattern sustained by gravity and the mass spread through visible and dark matter. Our motion through this system is gentle on human timescales. Day to day, nothing in the sky tells us we are on a moving platform. Earth's spin makes the sun rise and set. The annual orbit makes the constellations shift over the seasons. Beyond that, the change is too slow to notice, without precise tools or long records. That is why early skywatchers called the stars fixed. They are not fixed, but they move so slowly relative to each other from our point of view that for a lifetime, they might as well be. The way we came to understand the Milky Way grew from simple observations made under dark skies. Long before telescopes, people watched the sky closely. They tracked the repeating paths of the sun, moon, and planets. They noticed that some stars never set and others rose only in certain seasons. They grouped bright stars into patterns, constellations that matched their stories, their animals, their tools. These patterns were memory aids, a way to mark time and direction. Across many cultures, the band of the Milky Way earned names that match daily life: a river, a road, a trail of light. Without electric lights, the band was bright enough to cast soft shadows. Early thinkers tried to explain what they saw, using what they knew. Some thought the Milky Way was a feature of Earth's air, like a high cloud or a kind of light in the upper sky. The idea that the band was made of countless distant suns was not yet within reach. That took better instruments and a different way of thinking about distance. But the careful watching came first. It still matters, even today. If you go far from city lights and let your eyes adjust, the Milky Way appears as a thick stripe with fine grain. You can see the dark rifts where dust blocks starlight and the knots where it shines through. Culture shaped the sky maps. The same patch of stars held different figures across the world, heroes and creatures in one place, tools and homes in another, yet the practical uses were similar. Sailors used the rising and setting of certain stars to guide across oceans. Farmers used the first evening appearance of a bright star to plan, planting, or harvest. Priests and calendar keepers linked sky cycles to festivals. The sky was a stable frame against which life moved. Think of lying on a hillside without city glow. The air cools, sounds are small. The Milky Way lifts and arches overhead. At first, it is a blur. Then, as your night vision improves, it gains texture. You can tell the difference between a rich star field and a thin one. You can pick out bright clusters with the naked eye. You become sensitive to motion so slow it only shows over hours. The band rises, tilts, and drifts. Stars near the horizon twinkle and wink as the air shakes their light. Higher up, the points are steadier. Without clocks, you could still keep time by these changes. Night after night, the patterns return, shifted a little. The shift is because Earth moves around the sun, changing our view of the background sky. Over many months, a given constellation sets earlier in the evening, then vanishes into the sun's glare, then returns before dawn. Over many years, careful watchers notice that some stars drift compared to others. That slow drift, called proper motion, is the fingerprint of real movement through space. But to the eye in one sitting, the biggest effect is the steady westward drift as Earth turns. You could spend hours tracing them, watching how they drift slowly westward through the night, how they return, night after night, in slightly shifted positions. Patterns begin to show themselves with practice. Bright clusters, like the Pleiades, a small tight group you can pick out with the eye. A red point, like Antares, a swollen, cool star in Scorpius. A faint blur that we now call Andromeda, that blur, is not a cloud. It is another galaxy, the nearest large one to ours, but so distant you could cover it with your thumb. In the neighborhood of night, distance hides in plain sight. Ancient observers did not know what stars were, but they sensed the sky mattered. The regular rhythm of the heavens brought calm. On Earth, seasons shift, weather changes, and lives rise and fall, yet the stars return. That stability suggested that the universe had order. Within that order, people looked for patterns and links, hoping the sky and the ground spoke the same language. They learned to measure and count. They made records and predictions. Curiosity turned, slowly, into science. The sky was no longer only decoration. It became data. When Galileo aimed a small telescope at the Milky Way in 1609, the view changed for good. The hazy band resolved into countless points of light. Those soft white lanes were not vapor. They were distant suns beyond counting. This was direct evidence that the cosmos was larger than anyone had guessed. What had seemed like a local glow was a deep field, thick with stars. Galileo sketched what he saw. Clusters so dense, they looked like spilled grains. Even so, his instrument showed only a thin slice of what is there. Today, we know that when you face the Milky Way, you are seeing a fragment of one spiral arm. Our solar system sits inside a spur called the Orion Arm, between two larger arms. When you look at the glowing river of stars, you are sighting along the length of this arm through gas, dust, and light. It is like looking through fog at night. You can pick out the nearest lights, but not the full shape of the city around you. The rest of the galaxy extends well beyond the reach of your eyes, wrapping us on all sides. Our view is blocked by the very material the galaxy is made from. We are within the glow, trying to see outward from inside. This makes the scene deceptive. The sky flattens depth into a dome. Two stars that look close together may be hundreds of light years apart. The patterns we name Orion, Cassiopeia, the Big Dipper are lineups that exist only from our position. Move a few hundred light years in any direction and those figures break into unrelated points. The sky we grow up with is an effect of where we stand, yet it is a shared effect. Every culture has seen that same dome and traced its own shapes, turning a common view into a bridge between imagination and the wider universe. There is a quiet comfort in knowing that the light reaching your eyes left long before you were born. Some photons have been traveling for centuries. They crossed cold space and arrive for an instant on your retina, then vanish. Each night sky is a mosaic of ages. Some stars have already died. Their last light is still on the way. Others are only now forming inside clouds of gas and dust so thick that visible light cannot escape. Although the sky looks still, it is a field of motion and change. Night itself is simple. It is the side of Earth turned away from the Sunday. Our planet's shadow extends into space, and that shadow grants a view outward. The stars are there at noon as well, but daylight hides them. When the sun sets, a window opens. Through it, we see a small patch of our galactic city. We live in a quieter district, well away from the crowded core. That calm may have helped life take root here. Near the center, radiation is stronger and orbits are more chaotic. The environment would be harsher for a fragile biosphere. In that way, the suburbs of the galaxy may be part of why our nights are peaceful. If you could travel far from the solar system, the constellations would dissolve. New patterns would appear. The sun would fade to a faint point among billions. Earth would be invisible. All the stars you can see with the naked eye would fit inside a tiny patch of sky. That is how local our unaided view really is. The rest lies beyond without instruments. Even so, that small patch of light holds the sky that shaped human culture. The visible night is the most personal slice of the galaxy. Mapping beyond it is hard. Dust in the Milky Way blocks visible light along the plane of the disk. Astronomers use radio waves and infrared light, which pass more easily through dust, to see into hidden regions. Over time, these methods have built a rough map. It is a working sketch made from inside a fog, a bright central bulge, a thin starry disk, spiral arms curling outward. The sun sits about halfway from the center to the edge, orbiting in the disk. As instruments improve, the map gains detail. We find stellar streams, long trails left by smaller galaxies that the Milky Way pulled apart and absorbed. We trace faint shells and ripples from past mergers. The galaxy is dynamic, shaped by buildup and mixing. We identify star-forming regions, vast cold clouds glowing softly in infrared, where gravity draws gas together until new stars ignite. We find globular clusters, compact groups of ancient stars that orbit in the halo like distant satellites, relics from the early days of our galaxy. Evidence shows the Milky Way has consumed many small companions. Their remains are spread across the sky like fingerprints. Space between stars is not empty. It holds very thin gas, mostly hydrogen, fine dust, grains, magnetic fields, and, on larger scales, dark matter. Dark matter does not give off light, but its gravity affects how the galaxy spins and how light bends when passing massive regions. The disk's spiral pattern traces places where density is higher and star formation is common. The glow you see is the combined light of hundreds of billions of suns, softened and filtered by this interstellar medium. It is tempting to treat the galaxy as a separate place, something out there to be visited. In truth, we are inside it and made from its materials. The starlight you notice has crossed the same gravitational field that holds you to the ground. The energy that runs your cells comes from chemical bonds formed from elements that earlier stars produced. Each breath carries atoms that once drifted between stars. Our shared origin does not remove the scale, but it turns scale into context rather than distance alone. Numbers help, but only up to a point. We can say the Milky Way spans about 100,000 light-years and is roughly 1,000 light-years thick in the thin disk. We can estimate its mass, count stars by sampling, and trace several main arms. Yet those facts do not match the feeling of standing under a dark sky. They do not describe how the view deepens the longer you look, or how thought slows as more stars come into focus. The city blocks of the night feel different depending on where you stand. In a city, sky glow dims the band to a faint wash. In the countryside, the Milky Way shows dark lanes, a bright central swell, and delicate edges fading into black. Under that kind of sky, it is easier to sense motion, to realize you are part of a turning system. The planet rotates, the stars drift. You are centered within a pattern you cannot feel, but you can learn to notice. That awareness has guided discovery. Many advances began with a small, careful observation. A slight wobble in a star's speed can signal the pull of an unseen planet. A faint smudge can reveal a cluster of thousands of suns. Dark patches can mark dense dust clouds where new stars are forming. The night is full of such clues, and we are still learning its layout. Think of the Milky Way as a city of stars. Our sun is a house on a quiet street. The nearest streetlights are the bright, nearby stars. Far off, The glow of the downtown bulge sits low on the horizon. Around it, districts and suburbs extend as a wide haze. The city turns. New lights come on as others fade. From our window, we see only a few blocks, yet the rest can be inferred. Somewhere else in that city, around a distant star, another observer might look up and ask the same questions. They would see the Milky Way from a different angle and perhaps a different arm. To them, our sun would be one faint point among many. They might never notice it. That symmetry is steadying. We are not central, but we share the same rules: gravity, light, heat, chemistry. The night sky is not a backdrop. It is the visible edge of a structure we live inside. When you face the Milky Way, you are looking along the border between what we have mapped and what remains out of reach. It is not beyond us. It is where we already are. As the solar system moves through the galaxy, the view changes on long timescales. Not tonight or next year, but across ages. Patterns will shift, star paths will evolve, and light will carry new information. Our map will grow. The sky we know is a snapshot in a long record, pulling your view down to earth again. It is easy to slip back into the feeling that our world is separate. We set our days by sunrise and sunset, not by the slow orbit of the sun around the galaxy. Yet every sound and color we know exists within this larger field. Earth is not the center. It is a small island in a wide sea of light. Seen from space, from far enough away to take in the whole sphere, Earth looks bright. Air scatters sunlight into a soft halo around the planet. From the surface, that light hides the broader universe. From orbit, the contrast is sharp. Oceans reflect sunlight like glass. Continents show pale tones from deserts, forests, and ice. The night side is not fully dark. Lightning flashes inside clouds, and cities trace fine nets of light. It is a delicate brightness, easy to miss at great distance, but clear once you learn its signs. Earth has a scale that suits us. We can circle it in hours, cross it in days, and photograph it as a whole. It has edges and regular cycles. Tides rise and fall. Seasons return. Even the drift of continents seems orderly when viewed from the planetary frame. Step beyond Earth's orbit, and familiar size cues fade. Oceans become streaks of color. Mountains flatten into texture. The air that shelters us thins to nothing. Farther out, the quality of light changes. Without air, shadows are sharp, and brightness falls off with distance from the Sunday space. Does not look like long exposure images. It is mostly black to the eye, with stars as steady points. There is no shimmer because there is no turbulent air to bend the light. The sun still shines, but smaller and harsher. Its light is not softened by an atmosphere. Surfaces show high contrast, brilliant on the sunlit side, black on the dark side. In that hard light, Earth would look fragile, a small world carrying thin air and liquid water. Astronauts describe a kind of calm shock at this view. Many say it changed them to see how thin the atmosphere is and how isolated the planet appears. From space, borders vanish. The world looks quiet and whole. What stands out most is the emptiness around it. Beyond the blue sphere is blackness, with no nearby planet or star to fill it. It is a small oasis in a wide, cold environment. Our world orbits a star we call the Sun, one among hundreds of billions in our galaxy. The Sun is a G-type main sequence star. That term simply says it is a stable, middle-aged star. Not too big, not too small. It has burned for about 4.5 billion years. and should continue for roughly 5 billion more. For us, it is everything. Its light powers weather and photosynthesis, and the chemistry that runs inside our cells. It is easy to treat it as unique, yet stars like the Sun are common. Many are smaller and redder, many are larger and bluer, but they all run on the same basic engine, turning hydrogen into energy. Sunlight crosses about 93 million miles, 150 million kilometers, to reach Earth in roughly 8 minutes. A sunrise looks immediate, but it is already 8 minutes old. The sparkle on water is a moment from the recent past. The warmth on your skin began in the sun's core, where pressure and temperature drive nuclei to fuse. Energy created there needs thousands of years to random walk from the core to the surface, then only minutes to arrive here. Each ray carries that long history before it touches you. Zoom out and the sun becomes one bright dot with a family of worlds moving around it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, plus dwarf planets and countless small bodies form a system bound by gravity. From above it seems neat and ordered. In truth, the gaps are vast. The moon feels far, yet you could line up about 30 Earths in the space between Earth and Moon. Mars, our next outward neighbor, can be more than 50 million kilometers away at its closest. Sunlight needs more than 4 hours to reach Neptune. A scale model helps. Shrink the sun to the size of a large orange. On that scale, Earth is a pinhead orbiting about 10 meters away. Jupiter is a marble nearly 50 meters out. The outer planets are tiny grains hundreds of meters farther still. The nearest star, our next stellar neighbor, becomes another orange more than 2,000 kilometers away. Between the two oranges, there is nothing but space. That is our local block of the galaxy, one star with its planets, separated by huge distances from the next system. Inside such emptiness, one small world developed life. The conditions had to line up. The right distance for liquid water at the surface, a magnetic field to deflect harmful particles, an atmosphere thick enough to hold heat, but not too thick to smother, and long stability so evolution could proceed. These ranges are narrow. They are also temporary. Yet on Earth, they held long enough for life to appear, adapt, and become aware. Awareness is rare as far as we know. The universe does not show a preference for life. It simply allows it when conditions permit. On Earth, the spark learned to look outward and ask where it came from. Daylight hides our view of that wider setting. The sun's light fills the sky and drowns out fainter stars. When Earth turns away at night, the wider field comes back into sight. The same light that sustains us becomes a veil during the day, and the fall of night lifts it around us. Hundreds of billions of other stars form the Milky Way's disk, and most likely many of them host planets. In that sense, our system is ordinary. Across the galaxy are older systems, larger systems, and stranger ones. Ordinary can be calming. We are not alone in structure, even if we might be alone in awareness. Smallness can clarify. When you see how little space Earth occupies, you notice how the same rules act everywhere. Gravity, radiation, and chemistry run the show across all scales. Hydrogen fuses in the sun as it does in stars near the galaxy's edge. Carbon in your body is the same carbon found in a distant cloud. Scale changes size and time, not substance. That continuity links us to every part of the Milky Way. Nothing here stands still. Earth spins once each day and orbits the sun once each year. The sun itself moves around the galaxy's center, taking roughly 230 million years for one loop. Our whole system rides along like a bubble in a river. We are never in the same place twice. Each second we travel thousands of kilometers relative to the galaxy, yet we feel no wind of motion. The air is carried with us. Space is nearly empty. The motion is smooth. From outside, our path is loops within loops within loops, each one set by gravity's simple math. There is no up or down in space, only directions and relative positions. The stars above are travelers too. Every star follows its own orbit around the galactic center. Over millions of years, familiar constellations stretch and skew. The shapes we know are temporary alignments, a chance arrangement seen from here and now. Yet to our eyes, the sky seems steady. The sun rises and sets. The seasons cycle. That reliability has guided how we live. It gave us calendars and planting times and the idea that nature has order. Underneath it all, slow change continues. The sun ages, the solar system drifts, and the galaxy evolves. If you have stood outside under a dark arch of the Milky Way, you have already watched motion at work. As night goes on, Earth's rotation carries you under the band. The pattern tilts and rises and slides toward the horizon. The stars feel like fixed markers, but it is you who turn. This simple motion links with larger ones, the yearly path around the sun and the long glide through the galaxy. The rule is the same at every level. Gravity sets the path, mass follows. Earth is both fragile and resilient. It is fragile because life depends on a thin film of air and water and a balanced flow of energy. It is resilient because it has outlasted impacts, ice ages, and extinctions. The sun could end life here with a modest change in output. It has instead held steady enough to support it for billions of years. The balance is narrow but real. When you look up, you stand on the one world known to support awareness. That fact does not have to feel isolating. It can feel like membership in a long process matter, learning to notice itself. Astronauts speak of Earth as a small blue light in a dark sea. The dark is not truly empty. It holds photons, dust, particles, and distant stars. From orbit, you can see the sun's glint on oceans and, beyond the planet, the faint stretch of the Milky Way. The sight reminds us that Earth is not alone in nothingness. It is embedded in a larger flow of energy and motion. The space between stars is not an absolute void, but an arena where light crosses all the time. Every beam of sunlight that warms Earth has crossed that arena. So has every soft reflection from the moon and every star you can see. To live in a galaxy is to be surrounded by light that is always on the way from somewhere. We may feel still, but we are not. The galaxy rotates. Its disk breathes as stars are born and die. Our world is a speck carried along in a slow, graceful turn. Smallness here is not a weakness. It gives us perspective. Because we are small, we can frame the vastness and measure it. Because we are fragile, we learn how balance matters. The Milky Way cannot know itself, but we can know it a little. Every image, every measurement, every careful look at the sky is the galaxy learning about itself through human tools. You can see the local part of this story with your eyes. Not every bright point at night is a star. Some are planets reflecting sunlight. They are members of our solar family, sharing the same star, moving along paths that do not cross, tied by the same gravity that keeps Earth in its orbit. We give them names, send probes, and map their surfaces. Still, they are far. We can see them, but not touch them by hand. The nearest world is the moon. It feels close and familiar. It shapes our tides, steadies Earth's spin, and lights the night. Yet it is nearly 400,000 kilometers away. Light takes a little over a second to cross that gap. On a simple model, if Earth were a basketball, the moon would be a tennis ball about 7 meters away. Between them is true vacuum, no air, no sound. The first travelers there spoke of looking back at Earth and covering it with a thumb. Their ship took about 3 days to cross the emptiness. The moon is the closest world, and already it lies beyond everyday human sense. Beyond the moon, the scale grows quickly. Venus can come within about 40 million kilometers. Mars can come within about 55 million kilometers when orbits line up. Numbers this large blur, so it helps to think in light time. Light needs about 3 minutes to travel from Mars to Earth at a favorable alignment. A radio signal to a rover is a message to the past. By the time the machine hears it, Earth has moved on. We see the planets not as they are right now, but as they were minutes ago, sometimes hours. The farther we look, the older the view becomes. The sun is 8 minutes behind our present. Jupiter is tens of light minutes away. Neptune is about 4 light hours distant. These delays turn the solar system into a map of time as well as space. The idea can feel strange at first, but it is simple. Light is fast, yet not instant, and space is large. Even with delays, we still call these worlds neighbors. The word helps. It brings the scale down to something we can hold in mind. For thousands of years, those wandering points were the only other worlds we knew. Early astronomers watched them move against the fixed star background and named them planets, from the Greek for wanderers. They did not know what the wanderers were, only that their motions were different. Over centuries, careful observation showed that they are other worlds, reflecting sunlight like Earth. Mercury is the smallest and fastest, hard to see except at dawn or dusk. Venus, wrapped in cloud, shines brightest and is often mistaken for a new star on the horizon. Mars glows a steady red, a small ember among the constellations. Jupiter and Saturn move more slowly, their orbits long. Through a telescope, Jupiter shows bands and storms. Saturn shows rings wide, thin sheets of ice and dust, spread across hundreds of thousands of kilometers. These sights, once hidden from naked eyes, expanded our sense of what a world can be. When Galileo turned his telescope to Jupiter, he recorded 4 small points near it that shifted night by night. They were not background stars. They orbited Jupiter. This was clear evidence that not everything moves around Earth. It was a turning point. The sky was not a fixed dome. It was a system, layered, connected, and wide. Each new discovery since then has added another layer of scale, each one reminding us how small our own orbit really is. If we step farther out, the planets feel less like companions and more like distant cities linked by weak, delayed signals. The Voyager spacecraft, launched in 1977, are still heading outward. They flew past the giant planets and continued on. Both have crossed into interstellar space, beyond the sun's protective outflow called the solar wind. Each carries a golden record, a small curated message from Earth, meant for any finder who can play it. Today, they are more than 23 billion kilometers from home. A signal from them takes over 20 hours to reach our antennas. Every transmission is a whisper from beyond sight, a report from a place no human has visited. Distance changes meaning out here. On Earth, we measure distance by travel time, roads, and vehicles. We imagine bridges and flights and satellite links. Outside the atmosphere, there are no bridges and no shortcuts. Space is not a medium that helps you along. It is the near absence of matter. Each kilometer is simply more void. What connects us across it is light. Light is the messenger and the measuring stick. It carries information from the sun, the planets, and the stars. It tells us what exists where we cannot go. A telescope catching light from Saturn's rings is catching photons that left the sun more than an hour earlier, bounced from bright ice, and then traveled another long stretch back to us. This happens everywhere, all the time, building a silent web of information across the solar system. Light carries details: the chemistry of an atmosphere, the temperature of a surface, the presence of clouds, storms, and hazes. Without reflected or emitted light, the planets would be dark. They do not shine on their own. They borrow the sun's light and return a fraction of it. In that sense, the solar system is a hall of mirrors, sharing one lamp. Venus looks brilliant because thick clouds reflect most sunlight. Mars looks dimmer because its dark, iron-rich soil absorbs more. From these reflections and from close-up probes, each world shows a distinct character. Mercury is airless and extremes-driven, baking by day and freezing by night. Venus hides a crushing, hot surface under permanent cloud, an intense greenhouse. Mars is cold and dry now, but once hosted rivers and lakes. Jupiter is a deep atmosphere in motion, with bands and a storm, the great red spot larger than Earth. Saturn is colder, ringed with ice and dust, and surrounded by moons of many kinds. Uranus and Neptune are ice giants, pale blue and windswept, far from the sun's warmth. Together they form a family: 8 major planets, dozens of major moons, and countless small bodies, all circling the same star. Compare sizes, and Earth looks modest. Jupiter could hold more than 1,000 Earths. The Sun could hold 1,000,000. Yet Earth's modest scale helps. Gravity and heat balance to allow liquid water, weather, and long-term stability. Seen from above, the solar system is ordered, but its order lives inside immense distances. The inner planets move fast, the outer move slow. All follow orbits set by gravity. The pattern is calm to our eyes, yet everything interacts. Giant planets nudge comets and asteroids. Resonances in the asteroid belt arise from Jupiter's pull. A comet passing near a planet can be flung inward toward the sun or ejected outward. Nothing is truly alone. Even across billions of kilometers, the geometry of gravity links the parts. Technology has let us explore this neighborhood with machines. We have flown orbiters around every major planet. We have landed on Venus, Mars, Titan, and comets. Cameras have watched blue sunsets on Mars, methane rain on Titan, and lightning inside Jupiter's clouds. Each image is a postcard sent across millions or billions of kilometers. The signal that brings it has crossed a hostile medium, weakened by spreading, touched by cosmic rays, and still arrived usable. It is a small miracle repeated thousands of times. Even so, these distances are small compared to the gaps between stars. Proxima Centauri, the nearest star to the Sun, is a bit more than 4 light-years away, about 40 trillion kilometers. Traveling as fast as the Voyager probes, a crossing would take over 70,000 years. That is our true local scale, a tight cluster of worlds around one star, and then a gulf so wide that the next star might as well be a separate island universe. The gap is not empty of physics. Starlight crosses it. Gravity acts across it. Cosmic rays pass through it. But for now, it is beyond our reach by travel. Past Neptune, sunlight thins, warmth fades. The sun becomes a sharp, bright point, not much larger than other stars to the eye. The familiar realm of thick atmospheres and active weather gives way to something quieter. The outer solar system is not empty though. It holds the leftovers of formation, icy bodies, dust, and rock. Much of what did not become planets was pushed outward by gravity and radiation pressure billions of years ago and settled into wide, thin populations. The first of these is the Kuiper Belt, beginning just beyond Neptune and extending billions of kilometers outward. It is a zone of small, frozen worlds with slow, long orbits. Pluto, Eris, Haumea, Makmak, and many others live here, dwarf planets among a crowd. Pluto's reclassification came when we learned it is one of many similar objects. Its discovery in 1930 was a triumph of careful comparison on photographic plates. Even then it was clear how remote it is. Sunlight there is about 1,000 times weaker than at Earth. Its day is about 6 Earth days long. Its year spans more than 2 centuries. If you stood on Pluto, the sun would be a bright star, not a disk you could warm yourself by. New Horizons reached Pluto in 2015, after nearly a decade of flight. The pictures showed mountains of water ice, plains of nitrogen ice, and a thin atmosphere that forms hazes. Pluto is small and cold, but not inert. Slow processes still shape it. After that flyby, the spacecraft continued into the Kuiper Belt and imaged another object. It is still moving outward, studying a region we had only modeled before. Farther out, the sun's influence fades more. The solar wind charged particles flowing from the sun grows weaker with distance. Eventually, it meets the thin gas between stars and slows to a stop at a boundary called the heliopause. Beyond this, the interstellar medium dominates. The Voyager probes crossed the heliopause years ago. Their instruments saw the change as the solar wind vanished and a different population of particles and fields took over. They now drift through interstellar space, carrying a small record of our planet. Beyond the Kuiper Belt lies a much larger, spherical swarm called the Oort cloud, probably extending tens of thousands to perhaps 100,000 astronomical units, AU, from the Sunday. 1 AU is the average Earth-Sun distance. The Oort cloud is the likely source of long-period comets. Occasionally, a passing star or the tidal pull of the Milky Way perturbs an object there, sending it on a long inward fall near the sun. Ice vaporizes and forms a tail. Most of the time, these bodies remain frozen and dark, orbiting quietly for billions of years. No spacecraft has ever reached the Oort cloud. We infer its existence from the paths and periods of comets we observe. If you could stand on an Oort cloud object, the sun would be a bright point scarcely different from the brightest stars. The boundary between solar system and galaxy would blur. The sun would still hold you in a weak grip, but the pull of other stars and the general mass of the Milky Way would be comparable. The edge of our system is not a sharp wall. It is a gradual fading from the domain of one star to the shared field of many. The darkness here is not a threat. It is simply low density. Energy is spread thin. Still, add up the faint light of the galaxy's hundreds of billions of stars, and there is a soft background glow. If your eyes were sensitive enough, you would see it as a haze, From Earth, that collective glow is the Milky Way band. From within, the galaxy is less a set of points and more a gradient, denser toward the center, thinner toward the edge. We live in a quieter, thinner region. Past the Oort cloud, the sun no longer sets the tone. Space belongs to the galactic field. The gravity from the sun, from nearby stars like Alpha Centauri, and from the distant bulge all blend into one slow influence. The darkness becomes shared space. Keep moving, and nearby stars would eventually come into range, though nearby still means many light years. Proxima Centauri is just over 4 light years away. Between us and it lie a few atoms per cubic centimeter, charged particles riding magnetic fields, and occasional dust grains. You would not see much with your eyes, but instruments would register structure, faint shocks from ancient supernovae, ripples in density, and the directions of magnetic lines. The interstellar medium is not still. It flows. Shock fronts compress clouds and may seed new stars. Magnetic fields guide charged particles. High-energy cosmic rays pass through all the time. Our picture of the outer solar system and the nearby galaxy keeps improving. Radio and infrared telescopes see through dust. Space telescopes avoid atmospheric blur. Deep surveys map stellar streams, the stretched remains of small galaxies, merged into the Milky Way. These streams arc across the sky, evidence that our galaxy grows by gathering smaller systems. The more we look, the more we find fine structure, shells, ripples, and faint clouds, marking ancient events. Each new layer of detail pushes the boundary of what we consider local farther out. From up close, the solar system feels complete. From a little farther, it becomes a subsystem of something larger. Light ties it together. Gravity binds it. Motion carries all of it through space. Each planet, each comet, the dust between them, everything shares the same overall path around the galactic center. Our group of worlds is one thread in a wider pattern of matter and light. Distance gives these worlds room to be themselves. It lets each keep its own weather, chemistry, and colors. It also gives us perspective. If the nearest planets are separated by tens of millions of kilometers, how wide must the galaxy be? And yet we can still point to them, identify them by eye, and follow their motions. Distance does not erase familiarity. It deepens it by requiring patient observation. Past Neptune, the sun's light feels hard and far. The solar wind weakens. The heliopause marks where the sun's influence yields to the galaxies. Beyond that, the field is communal. The Milky Way's gravitational shape, the tug of passing stars, and the drift of gas and dust set the scene. Light still travels, bringing news from everywhere, even if most photons go uncollected and pass on forever. Think of this region as a transition, not a border, but a blend. The Kuiper belt, the scattered disk, the hypothesized Oort cloud, the interstellar medium. Together, they are the outer fabric of our home system and the inner edge of the galaxy. We cannot walk there, but we can measure it. Instruments feel the change in particles, fields, and radiation. Probes cross boundaries and report back. Models meet data and improve. What once seemed like empty space becomes a structured environment. This shift in view echoes our history. For a long time, humanity treated the solar system as the entire cosmos. The idea of other suns with their own planets was a bold thought experiment. Even after telescopes revealed star clusters and fuzzy patches, the scale was hard to grasp. But with better optics, better detectors, robotic explorers, and careful math, we kept expanding the frame. Each step outward made the next step imaginable. The boundary of what we call nearby moved from the moon to Mars, to the outer giants, and then beyond the heliopause, into the general field of the Milky Way. Little by little, with signals as thin as a whisper and images built photon by photon, the boundaries expanded. You can think of what once felt infinite as only one layer of a larger scene. The farther we extend our view, the less an edge makes sense. Scale simply keeps opening. Imagine drifting past the last familiar objects of the solar system until the sun behind you softens into the general starlight, and the Milky Way spreads ahead as a thin, bright disk about 100,000 light-years wide. You haven't really left anything. You've entered a wider frame where the darkness is not isolation, but membership at a larger scale. Every small point around you is a star. Most likely it has planets. On some of those worlds, minds may be asking the same questions we are. Deep space between the planets is extreme temperatures only a few degrees above absolute zero, and a constant drizzle of radiation from distant stars. But it is not useless or empty. Over millions of years, thin dust gathers into thicker clouds. Gravity squeezes pocket after pocket until a core heats and a star turns on. Around that young star, a disk of leftover gas and dust flattens, clumps, and builds planets. What looks like emptiness is a workshop, slow but steady, making the next systems that will shine and orbit. If you could hold the whole picture at once, the sun dim behind you, nearby stars ahead, long filaments of gas linking one region to another, you would feel inside something active and continuous. In every direction there would be faint light and slow motion. Beyond would lose its edge, because there is always more. In the galaxy, the space between stars is not a border. It is the shared medium everything lives in. Time itself feels different here. There is no sunrise to reset the clock, no weather to mark a day. You might count time by a pulsar's steady radio beat, or by the slow change in the pattern of neighboring stars. Things move, but on human scales the scene seems still. Over 10,000 years, constellations shift a little. Over 1 million, shapes start to stretch, distance deepens, and so does time. Even in that vast quiet, traces of us exist. The sun's light keeps expanding outward as a faint sphere, and inside that sphere are our signals, early radio, spacecraft calls, radar pings thinning out as they go. They will fade into noise, but for a while they mark a small, curious species that lived around a yellow star. Fragments of our system move outward too. Pebbles, icy bodies, and dust grains carry the sun's chemistry with them. Far enough from home, those small things are simply part of the Milky Way. The edge of the solar system is not a wall. It is a gradual handoff from the sun's control to the galaxy's wider pull. The sun's light fades, and other starlight replaces it. Planetary orbits give way to galactic motion. There is no click of crossing, only the sense that the ruler you use must grow. Go deeper still past the last warmth into darkness that has its own character. This darkness glows very softly at a temperature of about 2.7 Kelvin. That glow is the cosmic microwave background, the stretched out light from the early universe. It is the oldest light we can see, a memory from a time before stars formed. So even far outside the familiar, you meet the beginning of everything written into the background. And yet all we know returns to one ordinary star. We use a different name for it because it is ours. We call it the Sunday. It is not unusual in the catalogue of stars, not very big, not very small, but for Earth, it is decisive. Without it, no ocean, no air like ours, no life. When you study the sun, you are not looking at a simple bright circle. You are studying the power source of our world, the center of the system that holds us, and a steady engine that has burned for more than 4 billion years. From afar, it would be only a modest point. Up close, it fills the day and sets the rhythm of almost everything living here. The sun spans about 1.4 million kilometers, over 100 Earths across, and holds 99.8% of the solar system's mass. It is a globe of plasma, a charged gas that flows and churns. The photosphere, the visible surface, is about 5,500 degrees Celsius. Deep inside, at more than 15 million degrees Celsius, hydrogen nuclei fuse into helium. Fusion releases energy that random walks outward for thousands of years. When that energy finally escapes as light, it crosses space in 8 minutes and reaches Earth. That light powers photosynthesis, drives winds and currents, and keeps water liquid across much of the planet. Almost every form of energy we use ties back to this source. Plants store sunlight in chemical bonds. Fossil fuels are ancient sunlight. Wind and waves form from uneven solar heating. The sun dominates our energy budget, and it does so with rare steadiness. Gravity's inward pull balances fusion's outward pressure in a long-lived equilibrium. That stable balance is why complex systems can grow and persist. If the sun's output swung wildly, climate would lurch and stability would fail. Its reliability is the quiet baseline for life. Steady does not mean static. The sun's surface and atmosphere are active. Magnetic fields arch into space, carrying loops of hot plasma. Cooler, darker sunspots appear and vanish. The outer atmosphere, the corona, reaches millions of degrees and flows outward as the solar wind. That wind drags the sun's magnetic field far into space and shapes conditions around every planet. When the sun releases flares or coronal mass ejections, bursts of energy and particles rush outward. Earth's magnetic field catches many of those particles and guides them toward the poles, where they light the sky as auroras, visual proof that we live under a star's influence. Inside, the sun is mostly hydrogen, with helium and a small fraction of heavier elements. By fusing hydrogen, it converts a little mass to energy every second, about 4 million tons, by E equals mc squared. Even at that rate, the fuel lasts. The sun should continue core hydrogen fusion for about 5 billion more years. After that, the core's hydrogen runs low, gravity gains ground, and the star changes. The core contracts and heats. The outer layers expand. The sun becomes a red giant. Mercury and Venus will be lost. Earth may be engulfed or baked into sterility. After a few 100 million years in that swollen state, the sun will shed its outer layers to make a glowing shell, a planetary nebula, while the core becomes a white dwarf, hot, dense, and fading over vast time. The sun's atoms will then mix into the interstellar medium and help build new systems. That future is distant, but the path is set by the same rules that hold today. Stars like the sun regulate themselves. If fusion runs too fast, pressure rises, the core expands, and the reaction cools. If fusion slows, gravity compresses the core, heating it and raising the rate again. This thermostat keeps output within a narrow range for very long spans. Simple rules, gravity, pressure, temperature, can build long-lived order. The universe's complexity rests on such platforms. Our daily view is shaped by motion. The sun seems to cross the sky because Earth turns. The sun also spins roughly every 25 days at the equator and more slowly near the poles. That uneven spin twists magnetic fields and sets up energy releases like flares. Solar activity rises and falls in cycles that average about 11 years. These cycles affect the space around Earth radio noise, satellite drag, even geomagnetic storms that can push at power grids. The link between Earth and Sun runs through light, particles, and fields, not just warmth. The sun's place in human culture is as deep as its physical role. People have honored it, feared it, timed their lives to it. Myths of dawn and light reflect a real dependence. Sleep and alertness, migration and growth all track sunlight. Our bodies run on circadian rhythms tuned by the day-night cycle. Learning that the sun is a nuclear fusion reactor does not lessen awe, it adds detail. The ray that warms a window is the end of a chain that started in the core with nuclei merging. Food webs begin with photosynthesis. Even ecosystems that rely on chemical energy at deep-sea vents fit inside a planet shaped by solar heating above. The sun is also our clock. Sundials, calendars, solstices, and equinoxes all measure our geometry with it. Earth's tilted axis makes seasons by changing the angle and length of daily sunlight. Our sense of days and years comes from this steady movement. Variation gives time meaning. Without it, the idea would float. Solar light covers many bands: visible for sight, infrared for warmth, ultraviolet that can harm in excess. Earth's ozone layer blocks much of the UV while letting enough through for useful chemistry. Survival sits in balance again. Too little energy and Earth freezes. Too much and it burns. We live in the narrow zone, where light supports liquid water and complex life. The sun shapes each planet differently. Mercury bakes and freezes without air. Venus traps heat under thick clouds, becoming hotter than a kitchen oven. Mars receives less energy and, with little air, is cold and dry. Farther out, giant planets still feel the sun's reach in their upper atmospheres and magnetospheres. Across the system, the solar wind carves a bubble in space. At the edge of that bubble, the heliopause the wind yields to the thin gas between stars. The boundary is where the sun's influence blends with the galaxy's field, not a hard border. The wind carries a record of the sun's activity outward, like a faint wake behind a boat. The sun is moving, too. It orbits the center of the Milky Way in roughly 230 million years, carrying every planet and moon with it. From our deck, the sun seems still and central. From the galaxy's point of view, it is one traveler among many, sliding along a slow path set by gravity and mass, spread through stars, gas, and dark matter. To call the sun our star is to admit a bond rather than a claim. It is the center of our system and part of who we are. All people have depended on its light and warmth. We evolved under its spectrum. Our eyes are tuned to it. Our biology keeps time by it. Without the sun, we would not simply be cold. We would not be possible. Knowing there are countless other stars does not weaken the bond. It sharpens it. This is the star that fills our days, sets our seasons, and powers each leaf and heartbeat. It links the smallest details molecules inside cells to the largest cycles, stellar fusion, and galactic motion. The sun is not only above us, in the elements that make our bodies and in the energy that moves through our lives, it is within us. As we widen our sense of home, we include the star itself, the stable center that binds our system. And as the solar system moves through the Milky Way, that star carries us forward, its gravity holding the pattern together. We ride with it, protected by its warmth, powered by its light. Think about how numbers feel in your hands. We count apples, buses, people in a line. Even when we push into thousands, the picture stays inside our reach. The Milky Way breaks that habit. Here, counting becomes less like arithmetic and more like acceptance. Astronomers estimate between 100 and 400 billion stars in our galaxy. The range is wide because dust hides much of the disk. Many stars are faint, and we can only sample patches and scale up. Even the lowest figure is already past ordinary meaning. A single clear night shows you only a thin slice of a neighborhood, perhaps 2,000 or 3,000 stars above the horizon, 5,000 at most for the entire sky under perfect darkness. That is not a percentage worth writing. It is a reminder that the sky looks crowded only because our eyes resolve the nearby and the bright. Behind those points, the density rises invisibly. The band of the Milky Way is the sum of countless distant suns whose light blends into a soft glow. Early observers met the limit quickly. Each improvement in optics revealed more stars behind the stars, as if the background had no end. Modern surveys expanded the effort with detectors and computers, but the lesson stayed the same. The more precisely we count, the more countless it becomes. New instruments do not finish the tally. They widen the stage. It is not just how many, but what kind. Stars span a broad spectrum of sizes, colors, and lifetimes. Most are smaller and dimmer than the sun, red dwarfs that sip fuel and can burn for trillions of years. A few are massive and bright, racing through their fuel in a few million years before collapsing or exploding. Between lie yellow, orange, white, and blue stars with different temperatures, masses, and fates. Our sun sits in the middle, not exceptional, but stable part of the steady majority that keeps the disk luminous over long ages. Look at the Milky Way with the unaided eye, and it appears as a pale, irregular band, a river of light. Through a telescope, the blur resolves into points. Galileo was the first to describe that transformation in detail, writing that the cloudy strip resolves into innumerable stars. Innumerable is the right word. It marks the moment where number stops being a picture and becomes a feeling. If every star were bright enough, night would never be dark. It is dark because most light is too faint or too far, and because dust absorbs and scatters it. Darkness is not emptiness. It is light thinned beyond our threshold and stretched across time. Counting stars directly is not possible, so astronomers count mass. They estimate the galaxy's total mass in stars, divide by a typical stellar mass, and infer a number like weighing a forest instead of counting trees. It gives scale, but not a scene. Try the naive method. 1 star per second would take hundreds of centuries, and during that time, births and deaths would change the total under your feet. The galaxy does not pause while we list it. Many of those billions belong to families. Roughly half of all stars live in binaries or higher multiples, orbiting a common center. Others gather temporarily in clusters, tight globulars in the halo, and looser open clusters in the disk. Around many stars are planets, debris belts, and dust. In recent decades, Observations have confirmed thousands of exoplanets by watching starlight dip as a planet crosses, or by measuring tiny wobbles in a star's motion. From these counts and biases, the best inference is bold and simple. There are likely more planets than stars in the Milky Way. Hundreds of billions of worlds, each with its own temperature, air or none, and history. At that point, how many gives way to how they relate. The relations are dynamic. Stars are born inside cold, dense clouds of gas and dust. Gravity gathers a pocket. The core heats. Fusion begins. Radiation and winds blow away the nursery. Over time, groups drift apart under the broad pull of the disk. Some stars remain bound together for a while. Others wander alone. The process never stops. Creation and dispersal run together, keeping the city of stars supplied while its neighborhoods slowly change. In our sector, inside a modest spiral feature called the Orion Arm, stars are separated by light years. That sounds close until you write it as distance, tens of trillions of kilometers. If the sun were a marble, the nearest star would be another marble thousands of kilometers away, with nothing solid in between. Multiply that spacing by hundreds of billions, and you glimpse the structure, mostly space, threaded with points whose gravity and motion draw long, faint patterns. Spiral arms mark regions where those patterns gather. They are not rigid bridges of stars. They are waves of higher density, moving through the disk, compressing gas enough to spark new birth. Stars light up inside a passing arm, shine for a time, and drift onward. The arms are the memory of motion, not an assembly line frozen in place. In that sense, counting stars is counting process. Every number is a snapshot of paths already in progress. To map such a system from within, astronomers use the full spectrum radio telescopes tuned to the faint 21-centimeter emission from neutral hydrogen, tracing clouds that optical light cannot cross. Infrared reveals cooler objects and peers through dust. X-rays mark hot, violent regions near massive remnants or where matter spirals toward compact objects. Each wavelength exposes a layer. Stacked together, they form a composite picture, not a photograph of the whole forest, but a set of slices that, if aligned, outline the shape. Even with those tools, the picture keeps updating. The Gaia mission is measuring positions, distances, and motions for over 1 billion stars with fine accuracy, turning the static sky into a moving map. From that motion, astronomers reconstruct history. Streams of stars stretched across the halo, the ghostly trails of small galaxies long ago swallowed, ripples in the disk where past encounters stirred the stars, the rotation curve that hints at mass we cannot see. They can also project forward, showing how the pattern may shift in coming ages as we interact with neighbors like the Andromeda Galaxy. Counting becomes narrative, where the parts came from, how they flow, what they suggest about tomorrow. The uncountable nature of stars is also the uncountable nature of time. A star is not a fixed lamp. It is a stage of matter that begins, changes, and ends. Some are just igniting within dusty cocoons. Others are middle-aged and calm. Some are swelling into giants or shrinking into dense leftovers. White dwarfs, neutron stars, black holes. The disk holds all these ages at once. The light we receive mixes newborn blue with old red, 50 different histories arriving in the same beam. The dark lanes between bright patches are not empty either. They hold molecules, hydrogen, carbon monoxide, traces of more complex compounds, drifting and cooling until gravity calls them back. Those clouds are the raw material for the next generation. The galaxy is a recycler. The calcium in bones and iron in blood were forged in stars that lived and died before the sun formed. In that sense, numbering stars is also numbering ancestors. Remember the individual amid the total. Each star has its own path and possibility. Somewhere, a world circles a quiet sun and looks up, wondering. If minds exist there, they face the same failure of counting and the same expansion of context. Hundreds of billions of stars mean hundreds of billions of chances. Our place is less an exception and more a case within a broad pattern. The scale does not erase meaning, it frames it. Holding that scale steady in the mind can feel like leaning over a rail. Let the numbers loosen their grip and the scene becomes peaceful. Accept that the galaxy will not fit into a table and the effort changes. We move from tally to recognition, seeing the Milky Way as the environment that makes everything else possible. The uncountable is not a gap in knowledge. It is the natural result of size, time, and ongoing change. From Earth, the Milky Way we see is only a cross-section. A pale swath in the darkness becomes, in long exposure images, a textured arc of knots, lanes, and color. But that is an inside view of a spiral system. Our position roughly halfway from center to edge puts our line of sight along the disk through its densest plane. Every faint shimmer in that band is a part of the same structure turning through space. The galaxy is not a solid plate. It is a pattern held by gravity. Stars, gas, dust, and dark matter sharing motion. The spiral is not a painted shape. It is what happens when billions of orbits line up to make waves. The disk is about 100,000 light-years wide and roughly 1,000 light-years thick in its thin layer. Beyond the bright disk lies a halo of old stars and clusters, sparse and extended, and an even larger halo of dark matter, matter that does not glow but adds gravity. Seen from the outside, the Milky Way would look like a flat disk with a central bulge wrapped in diffuse light. The spiral arms, brighter swaths of higher density, curve outward from the center. They are places where new stars tend to form, but they are not walls. They taper gradually into the spaces between. Rotation is differential. Inner regions move faster than outer ones. That difference helps sustain the spiral wave. The result is a self-organizing shape, enduring as a pattern even as its parts come and go. At the heart sits the bulge, a crowded, elongated region of old stars and dust. Buried in that crowd is a supermassive black hole known as Sagittarius A*, with a mass of about 4 million suns. It occupies a compact volume, yet its gravity dominates the inner stellar motions. We cannot see the black hole directly, but we can watch stars whip around it in tight, fast orbits, their paths tracing the unseen mass. Most days, Skir A times is quiet, nibbling on small amounts of gas and dust, but sometimes it flares, sending brief outbursts of energy. The presence of such a massive object at the center now appears to be common in large galaxies, and the link between these black holes and the galaxies around them is an active area of research. The center is intense. Stars so close that some complete orbits in years or less, dense clusters interacting, clouds collapsing and heated by shocks. Dust makes direct optical views impossible, but infrared and radio instruments reveal a restless scene. Farther out, where we live, the disk is calmer. Stars are more widely spaced. Star formation is steady, but not frantic. The spiral arms pass like slow weather, a wave that takes hundreds of millions of years to roll by. Our Sun orbits the galactic center at roughly 26,000 light-years and moves around 200 kilometers per second. At that speed, one full circuit, one galactic year, takes about 230 million years. Since the solar system formed around 4.5 billion years ago, we've circled the galaxy roughly 20 times. Every orbit carries us through different regions: denser arms, quieter gaps, thin veils of dust, wider star fields, and the sky's pattern shifts so slowly that a human lifetime mistakes it for stillness. Yet on the scale of the Milky Way, change never stops. The disk itself is not a rigid plate. Its outer edge is gently bent, a subtle warp that lifts and dips across quadrants. That bend likely comes from long interactions, the pull of nearby dwarf galaxies, tides from the dark matter halo, ripples seeded by ancient mergers. Even without an atmosphere, a galaxy can ripple. Those waves move through stars and gas over millions of years, leaving faint oscillations we only notice when we compare careful measurements across the sky. This constant motion makes a large structure look unchanging. Stars ignite in the spiral arms, live through their phases, and end as winds or explosions that seed the surrounding gas with heavier elements. Supernova shockwaves sweep cavities clean, and at their edges, compress clouds dense enough to collapse again. The arms are more than pretty curves. They are the visible trace of a process, a record of star formation that has been repeating in different places for billions of years. Imagine rising far above the plane. The Milky Way would show as a dim, wide disk with a bright inner bulge. The arms would unwrap like pale smoke, strongest toward the center, thinning toward the rim. At that height, you would notice companions, two irregular satellites, the Large and Small Magellanic Clouds, swing nearby, bound by gravity and slowly reshaped by tides. Around the outskirts, you would also see faint star streams, long arcs left by small galaxies the Milky Way absorbed. Their stars, stretched into ribbons, still orbit as a memory of those events. Part of the spiral pattern we see today carries this history, a blend of order and leftover motion written into the disk. Drop back inside, and perspective changes. From our position in the Orion Cygnus spur, the arms that look like smooth arcs from above become lanes of brightness along the plane. Look toward Sagittarius, and the band crowds with light toward the center. Look toward the outer rim, and it thins to a gentle haze. Dark lanes thread the bright band, cold clouds that block visible light, yet glow in infrared, where their shapes appear as filaments and knots. In these lanes, you can read the balance at work. A dying star can clear a bubble, but the resulting shock can also trigger new birth along its rim. The Milky Way's cycle is not wasteful. Matter simply changes roll gas into stars, stars into ashes, ashes back into gas. It is tempting to picture arms as fixed roads, but they behave more like traffic waves. Stars drift in and out. The pattern persists because new stars keep igniting in regions of higher density, while older ones move on. The galaxy's rotation reveals another layer. The speeds of stars far from the center do not drop, the way planetary speeds fall with distance in our solar system. They stay close to constant. That flat rotation curve implies mass. We do not see dark matter forming a wide halo that outweighs the visible disk. The shape we admire rests on an unseen scaffold. Without that extra mass, the outer disk would not remain bound at the measured speeds. Even with mapping, much remains hidden. Dust in the midplane covers distant regions. The far side of the disk is inferred more than shown. Radio maps trace hydrogen across the plane. Infrared surveys pierce some of the fog. Gaia charts motions of closer stars with sharp precision. The picture is improving, but it is still a picture from within, built by stacking partial views. That incompleteness is not a flaw. It is part of what makes the Milky Way both studied and mysterious at once. Lie under a dark sky, and this all translates into a human scale. Every point of light is a participant in the same rotation. The sun's path carries us through arm and interarm regions, past thin gas and thicker clouds, and we feel none of it. The entire solar system is a small car on the outer lanes of an immense carousel. There is no grind of gears, just quiet, coordinated motion. If you could speed the galaxy up, you would watch arms coil and uncoil, clusters drift, bright patches flare and fade. At real speed, those changes only register in records that span ages. Think about the lineage inside that motion. The carbon, nitrogen, and oxygen in living things were forged in earlier stars. Some of those stars were born in an arm we once crossed, lived their brief lives, and ended with enough energy to send heavy atoms into space. Over time, that material cooled, mixed, and joined the cloud that made our sun and planets. The spiral is not only a pattern in space, it is a path through which matter cycles, the stage on which time moves matter from simple to complex and back again. Step 1. Layer outward, and the Milky Way becomes part of a group. Our local group includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen dwarf companions. From our vantage, Andromeda is a faint, elongated smudge to the eye under dark skies, but it is a massive spiral like ours, and it is moving toward us. On timescales of billions of years, the two main galaxies will interact, pass through each other's disks, and eventually merge. That future event will reshape both systems, puffing the disks into a new, more rounded galaxy. Stars are so widely spaced that direct collisions are unlikely. What changes is the shared gravitational field and the orbits within it. Planetary systems like ours may glide through the event untouched, but their night skies would evolve into a different arrangement of light. The local group itself lives on the edges of larger flows. Farther out lies the Virgo cluster, a deep collection of galaxies, and beyond that, an even larger pattern, an arrangement some call Laniakea, a basin of flow lines that shows how galaxies stream under the combined pull of their mass and the surrounding dark matter web. We do not need those names to grasp the point. The Milky Way is not isolated. It is one whirl in a field of whirls, each one moving, each one growing by collecting smaller neighbors, each one contributing to the map of gravity on larger scales. Return to our address and refine it. The Sun and planets sit about 26,000 light-years from the center, near the midplane of a disk, roughly 1,000 light-years thick. Our local interstellar environment is part of a bubble, a cavity carved long ago by supernovae that blew out and heated the gas. The Sun is near the edge of that bubble, moving into regions where the density changes slowly. Over millions of years, as we drift, the amount of interstellar matter along our path will vary, and that may subtly affect things like the heliosphere's size and how cosmic rays reach Earth. These influences are small on human timescales, but they remind us that our planet's setting includes more than our own star. The warp we mentioned earlier probably reflects the Milky Way's ongoing conversation with its satellites and with the mass in its halo. You can imagine the disk as a stretched membrane, tugged by passing companions and by asymmetries in the dark matter field. Those tugs set up waves. They travel across the disk slowly, and because stars feel gravity too, the wave is a feature of the whole system, not just the gas. Over long intervals, such waves can guide where clouds compress and where new clusters appear, adding another layer to the pattern. Meanwhile, the bar, a dense, elongated structure in the central bulge, channels gas inward along its length. That inflow can feed central activity and help shape the inner spiral arms. At the very center, the supermassive black hole, Sagittarius A*, anchors the inner dynamics. We do not see the black hole itself, but we see stars whipping around it in tight, fast orbits that betray its mass. Most days, it is quiet, with occasional flares as small amounts of matter fall in. Its presence seems to be part of a general rule. Most large galaxies host such a massive central object, and the growth of that object connects somehow to the galaxy's history of star formation and mergers. Out in our sector, daily life in the disk is calmer. Star birth proceeds at a steady pace along arms and in giant molecular clouds. Open clusters sprinkle the plain. Solitary stars carry their planets in wide lanes. The spiral pattern passes through like slow weather, a wave that takes hundreds of millions of years to cross our longitude. Our Sun orbits at roughly 200 kilometers per second. A full circuit takes around 230 million years. Since the solar system formed, we have made only about 20 laps. Every time Earth completes a year, the Sun has advanced a tiny step along its larger path. We are never exactly where we were. The background shifts too slowly for us to notice without instruments. The stability of our region matters. Near the center, stars pack tighter, radiation is stronger, gravitational encounters are more common. Far in the outskirts, the supply of heavier elements thins, and the raw materials for rocky planets may be less abundant. Between those extremes lies a broad zone where orbits are stable and elements are available. Some astronomers call this band a galactic habitable zone, not a strict ring with firm borders, but a useful idea that our position balances crowding and scarcity. Quiet lanes offer time. Time allows complexity. Our local neighborhood within dozens of light years contains familiar names. Alpha Centauri, with its 2 sun-like stars and a cool red companion. Sirius, bright and close. Epsilon, Eridani and Procyon, and Tau Ceti, each with its own mix of motion and, in many cases, planets. From those stars, the Sun would appear as a modest yellow point. The concept repeats. Every neighborhood looks ordinary from within, and each is part of the same disk. Between neighbors lies a medium that is thin by earthly standards, just a few atoms per cubic centimeter on average, yet not empty. It carries magnetic fields, shock fronts from ancient explosions, drifting molecules, and the faint glow of dust warmed by starlight. Even the empty parts of the sky belong to the galaxy's body. Above and below the plane, the halo extends tens of thousands of light years and hosts old stars and globular clusters. Those clusters follow long, looping orbits that carry them far from the disk and back through it. Some were likely born outside the Milky Way and captured during ancient mergers. Their distribution and motions trace a deeper history, how the galaxy assembled its mass, which directions it grew from, where it absorbed small neighbors. Out in the halo, astronomers also map stellar streams, ghostly lines of stars moving together, the remains of galaxies taken in and stretched thin. As the Sun continues its orbit, it will pass in and out of arm regions several times. Those crossings may correlate with subtle changes in the interstellar environment around us. A denser cloud might compress the heliosphere a bit. A stronger background of dust could change what reaches Earth's atmosphere. These hypotheses are under study. Their effects, if any, are small compared to the regular cycles set by Earth's tilt and orbit. Still, they show how large patterns can reach into local details over long times. It helps to translate our address into simple terms. Third planet from a G-type star, in the Orion Cygnus Spur, about 26,000 light-years from the center, orbiting within the thin disk, moving 220 kilometers per second relative to the galactic center, embedded near the edge of a hot, low-density cavity in the interstellar medium. Factual and plain, yet also a sentence of belonging. It names not only where we are, but how we move. Because we sit inside the system, every direction looks into it. The center lies towards Sagittarius, hidden by dust, invisible light, but blazing in radio and infrared. The rim lies opposite, toward Auriga and Perseus, where the band thins. When the Milky Way arches across a dark sky, we are looking along the plane, our line of sight cutting through layers upon layers of stars. The bright bulge region is not just more light, it is more of the disk stacked in that direction. The thin sections are where we look outward through less material. If you could leave the plane and look down, our solar system would disappear into the general glow. Even the most powerful telescope would need a map of motions to pick our star from the crowd. Yet all the familiar things would still be there. Oceans, forests, streets carried on a dot, moving with the rest. Scale would erase our outline, but not our place. No matter the distance, the Milky Way's light would include the Sun's contribution, tiny but present. The distribution of stars fills the galactic sea with texture. Near the bulge, stars crowd by the thousands in a cubic light-year. Out where we are, the average is a few per cubic light-year at most. That spacing creates the illusion of isolation while granting stability. Few close encounters mean orbits last for billions of years. Stability gives planetary systems time to settle, cool, and, in at least one case, host life long enough to become aware of the sky it lives under. Above the disk, globular clusters write the halo's old story. Below it, streams mark the paths of what arrived later. Around and through the hole, dark matter adds mass without light, setting the stage for how fast things turn and how far the disk can extend. The Sun's current lane is steady, but nothing is permanent. Over tens and hundreds of millions of years, we will sample different neighborhoods. The arm will pass, another will arrive. The sky's pattern will adjust a little with each slow turn. This view shifts our role from one of spectators to participants. We are not fixed, watching a universe revolve around us. We are embedded, moving, carried by the same rotation that guides everything we see. The galactic sea is an apt image because the Milky Way behaves like a fluid on large scales. Waves travel, currents form. Structures persist as patterns, not as objects. Our place in it is a small craft on a current we did not choose yet, one that keeps us safely in orbit. Stand on a world in a different arm, and the description would almost match ours. A star midway between hub and rim, a path that takes a few 100 million years to circle the center. Neighbors spread across light years, a faint band cutting the sky. An address in a galaxy without fixed markers is less a coordinate and more a relationship, how your motion sits inside the motion of the whole. Knowing our address gives scale without shrinking meaning. We are small and not central. We are also located in a lane that lasts, in a disk that has turned for more than 10 billion years, inside a group of galaxies that share a common space. Every familiar thing fits in that frame, one system among billions, each adding a tiny share to the total light. Integration, not prominence, is the point. We are part of the pattern that carries us, shapes us, and will keep moving long after our own chapter ends. As the slow rotation continues, the sky will change at rates the eye cannot track. Constellations pull apart, new alignments appear, arms drift past, faint streams brighten and fade with angle. Each galactic year adds a thin layer to the local story, then another. Somewhere within that rhythm, we keep our course. A small system in the Orion Cygnus arm, circling the center, surrounded by dust and stars and the faint glow of the disk. We cannot step outside for a full portrait, but we can read the interior view. Each clear night offers a cross-section of our home, a reminder that every pinpoint belongs to the same wide structure, turning on its quiet schedule through space. During and after that meeting, our home galaxy will still be moving through a wider flow. The local group itself drifts toward nearby mass concentrations, pulled along by gravity from clusters and superclusters stitched into the cosmic web. On these scales, motion comes from two sources at once: the overall expansion of space that increases distances everywhere, and local tugs that draw structures together against that expansion. Galaxies fall toward one another inside groups and clusters, even as the space between far-flung regions stretches. Both patterns act at the same time, and our path is the sum of them. To picture that layered motion, start with something close to home. The sun draws planets inward, setting their orbits. On a larger ring, the Milky Way's gravity turns our entire system around the galactic center. Larger still, the mutual pull of the local group sets the track of each member galaxy. Farther out, clusters gather along filaments, flowing toward dense hubs. And beyond all of that, the expansion of space increases the distance between widely separated filaments. Each layer adds a slow curve to the one below it, so every object traces nested paths, local circles riding on broader streams. Even when the view appears calm, evidence of this motion is written into the light. Starlight from within our galaxy shifts slightly in color as stars move toward or away from us. Light from distant galaxies is stretched by the expansion of space itself, shifting toward red in proportion to distance. Where gravity dominates, a galaxy's peculiar motion can partly cancel or add to that redshift. Where expansion dominates, redshift grows steadily with distance. In both cases, the color of light becomes a clock and a ruler. The structures that guide these motions are not random. On the largest scales we can map, matter forms filaments, sheets, and nodes with broad voids between them. The Milky Way sits along one of those filaments with Andromeda and their smaller companions, loosely connected to others through thinner strands. Along the filaments, gas flows into galaxies and fuels star formation. In the nodes where filaments meet, clusters of galaxies form, some with thousands of members. Between the bright structures lie voids so wide that a galaxy could travel for the age of the universe and never meet another. The pattern looks sparse, but coherent, with gravity as the only author needed. Closer in, the same physics arranges smaller patterns. Our sun moves not only around the galaxy but also through a region of warmer, thinner gas called the local bubble, likely carved by supernovae that erupted millions of years ago. The heliosphere, the bubble made by the solar wind, presses against that interstellar gas and changes size as the sun passes through denser or thinner patches. At Earth, these slow changes are too gentle to feel, yet they're part of the larger chain. Exploding stars shape the medium shapes the solar wind, and the solar wind shapes the space around our planet. Distances remain the hard part to imagine, so astronomers use a ladder of methods to make them usable. Very nearby stars yield to parallax, the tiny shift in apparent position as Earth moves around the Sunday. Farther out, characteristic brightness and spectral features act as standards. For very distant galaxies, redshift calibrates distance through the expansion law. It is not one tool but many, tuned to different ranges, each checked against the others where they overlap. That cross-checking adds confidence to a map we cannot see all at once. As maps improve, the Milky Way itself gains detail. Radio surveys outline hydrogen in the disk and trace spiral segments through the dust that hides them in visible light. Infrared views plot where stars form inside cold clouds. Measurements of stellar motion reveal ripples in the disk signatures of past nudges from satellites and ancient encounters. Even the disk's warp shows up as a pattern in star counts above and below the midplane, a gentle bend that rises on one side of the galaxy and falls on the other. None of this motion is dramatic on human timescales, yet over tens of millions of years, it adds up to the shapes we sketch. All stars ride these flows, and their lives add another rhythm. Small red stars burn slowly and may outlive the galaxy's present form. Massive blue stars burn fast and end in supernovae that return heavy elements to the medium. Those elements allow rocky planets to form and water to condense. In regions where stars are tightly packed, interactions are more common and radiation fields are harsher. In calmer lanes like ours, orbits can remain steady for billions of years. That difference in crowding is one reason our position matters. Stability gives time for complexity to evolve. The solar system's motion has its own small oscillations. Besides orbiting the center, the sun bobs above and below the midplane with a period of tens of millions of years, crossing the densest part of the disk and then traveling into thinner regions. Researchers have tested ideas about whether those passages correlate with conditions at Earth cosmic ray levels, comet flux, subtle climate markers. The evidence is mixed, and the effects, if any, are small compared with internal planetary processes. Still, the image of the sun moving like a boat over long swells remains accurate. Our orbit is a path on a sheet that is bent and rippled by gravity across great distances. Far from the disk, the halo carries the galaxy's oldest memory. Ancient globular clusters loop in long orbits that tilt far out of the plane. Stellar streams long, faint lines of stars moving together trace the remains of dwarf galaxies the Milky Way absorbed long ago. Each stream is a record of an encounter. Together, they form a scrapbook of assembly. Their motions help weigh the dark matter halo and map its shape. The halo's mass extends well beyond the visible edge of the disk, setting how fast the outer parts can turn and how strongly the galaxy responds to tides from neighbors. The center tells a different story. A bar of stars channels gas inward. The bar's ends feed inner spiral segments that curve toward the bulge. At the core, the supermassive black hole sits quiet most days, with short flares when small clouds fall inward, and heat the surrounding gas. Orbits close to that center run fast. Astronomers can watch individual stars swing around in a few years, and those tracks reveal the mass packed into the small, dark region. This is the same gravity that guides the entire disk, local and central at once, and its reach sets the tone for the innermost dynamics. Even while we map and measure, the Milky Way remains a participant in larger flows. The Andromeda merger is only one step. The combined remnant will continue along the filament, gathering smaller companions as it travels. Inside the remnant, new structures will appear, perhaps a thickened disk, perhaps shells and tidal tails, where stars were thrown onto wide orbits. From a planet like ours, the sky would shift over many generations, a second bright disk rising and stretching, a long period where two cores share the view, then a slowly settling halo with shells of light. None of it would be loud. The scale keeps every change wide and gentle. All of this sits within the larger trend of expansion. On the biggest scales, distances grow with time, and the light we receive arrives reddened by that growth. Nearby, gravity cancels the expansion and builds dense structures. Farther away, expansion wins and carries things apart. The line between these regimes is not sharp. It depends on mass and distance. That blend is why we can have a stable local group and still measure a general recession of far galaxies. It also means the universe has no single center. From any point, observers would see roughly the same large-scale pattern of receding galaxies, with the nearest regions showing the strongest local tugs. Motion at every scale leaves traces that instruments can read. Light bends as it passes massive objects, letting astronomers map gravity with arcs and stretched images. Background radiation from the early universe arrives with a nearly uniform temperature, but with tiny ripples that mark the first seeds of structure. Galaxy surveys show how those seeds grew into today's web. Stellar motions chart past disturbances in the disk. Even the solar wind writes a record in the outer reaches, where it meets interstellar gas. The sky is not only a view, it is a ledger. When the numbers get large, analogies help without pretending to be perfect. Think of the galaxy as a city, and our arm as a quiet lane near the suburbs. Think of the local group as neighboring towns along a river, drifting toward the confluence where two currents meet. Think of the universe as a fabric where the threads are filaments and the knots are clusters. These pictures miss details, but they keep the relations straight. Lanes feed boulevards, streams feed rivers, threads feed nodes. With that frame, distance becomes less an empty gap and more a context for motion. The marble and oranges model of the solar system shows how alone stars appear on a human scale, but the web model shows how joined they are on a cosmic one. The emptiness between stars lets light travel. The pull across that emptiness makes patterns. Both are necessary to the view we have and the place we occupy. Standing under the night sky, none of this complexity is obvious, and it doesn't need to be. The band arching overhead is enough to show that we are inside a structure vast enough to smooth individual motions into a steady glow. Every bright point participates in the same rotation, and every dark lane marks future light waiting in cold clouds. The Earth turns, the sun moves, the disk turns, the group drifts. There is no fixed point and no quiet center, only frames within frames where motion looks still because it is so even. If you could freeze the Milky Way for a moment and draw arrows on every star, gas, cloud, and cluster, the page would fill with vectors that curve and weave, but they would not be random. The arms would carry a slow flow of birth and dispersal. The bar would channel inward motion. The halo would show long loops around the core. Beyond, the local group would show two main arrows aimed toward a meeting. And beyond that, the arrows would lengthen with distance as expansion adds its share. Release the freeze, and the arrows would become paths, long, smooth routes traced over intervals that dwarf human eras. We live comfortably at one point along one of those paths. The parameters that describe it are plain: a nearly circular orbit at to 26,000 light-years from the center, a speed of a few hundred kilometers per second, a slow vertical oscillation through the disk, a residence near the edge of a hot, rarefied bubble in the interstellar medium. From these, other facts follow: a quiet, stellar density, a steady supply of heavy elements, a long window without frequent disruptions. None of this was chosen. It is simply where the initial conditions placed us. Yet from that placement came a planet where liquid water could persist, and a species that could look outward and piece together the pattern. As our instruments improve, we will watch more of the pattern in motion. New surveys will trace dust and gas with finer detail. Distances and proper motions will sharpen for more stars. Faint streams in the halo will grow clearer, and the warp's waves will resolve into specific crests and troughs. The catalogue of exoplanets will stretch to cooler, smaller worlds. The Milky Way's far side will emerge better in radio and infrared maps. Each edition will change the picture a little without changing the core. A thin, warped disk, a bright bulge and bar, spiral patterns of birth, a wide halo of old stars and dark mass, companions and streams at the edges, and a slow, steady rotation that carries all of it together. From our lane, the scene remains simple to the eye. A faint river of light marks the plane. A brighter thickening points to the center. A thinner stretch points outward. The details of motion and mass and history live inside those broad hints. They are not separate from the view. They are what the view means when translated into time and gravity. The same stars that make a smooth band at night are the actors in the processes that shape the galaxy at large. The same emptiness that makes them visible is the medium that lets their stories reach us. On the largest stage we can map, our galaxy does not travel alone. The Milky Way sits inside a flattened region called the local sheet, a slab of nearby groups that drift together. That sheet, in turn, slides toward the Virgo cluster, a heavy hub made of thousands of galaxies. Farther out, many of these motions join a deeper flow towards something bigger still, the region astronomers call the Great Attractor, hundreds of millions of light-years away. None of this is random. Gravity shapes matter into clusters, clusters into superclusters, and links them with long filaments. At every step, motion follows the same rule. Mass pulls, structures respond, and the pull combines across vast distances. Seen this way, rest is only local. You can stand still on the ground, but the ground rotates with Earth. Earth orbits the Sunday. The Sun circles the Milky Way. The Milky Way moves with other galaxies along a filament, and the filament itself follows the broader flow of the expanding universe. There is no single frame where everything stops. Stillness feels real because nearby things share our motion, not because motion has ended. These flows are slow on the scale of a life. Constellations hold their shapes for thousands of years, even as every star creeps along its own path. Over millions of years, the patterns will stretch and blur. New ones will appear. The sky we call familiar is a snapshot in a long movie. Its apparent permanence is a feature of our short view, not of the stars. Calling all of this drift can sound uneasy, but the drift is the order. Motion keeps systems balanced. Atoms vibrate, planets circle, galaxies turn. Gravity curves space and sets paths, and those paths distribute energy and momentum. The result is not chaos. It is a steady way for matter to avoid collapse into a single lump or a freeze into a static block. If you could watch the timescale speed up, you would see galaxies rotate and merge, clusters flex and shift, and arms of spirals brighten where new stars ignite. At full speed, these changes are quiet and continuous, a smooth current rather than a crash. Gravity's reach explains the calm. Every mass tugs on every other mass. The tug weakens with distance but never hits zero. Each star traces a curve through space-time, and those curves together form the geometry of the cosmos. On top of that sits the expansion of space itself. Inside groups and clusters, gravity wins and holds members together. Between distant clusters, expansion wins and increases the distance. This is not objects flying through an empty stage. It is the stage stretching. The farther apart two galaxies are, the faster their separation grows. That is why the universe has no single center. Expansion looks the same in every direction from every place. Astronomers describe this stretch by redshift. As space expands, light's wavelength stretches, moving toward red. The amount of shift tells us both how far the light has traveled and how much the universe has grown during the trip. When they plot many redshifts together, a pattern appears: filaments, sheets, and nodes of galaxies, with large voids in between. The Milky Way lies along one filament, with its neighbors drifting the same way. Our local motions ride on this larger flow. While the web sets the broad map, smaller motions run inside it. Stars orbit their galactic centers, planets orbit stars, moons orbit planets. Each scale nests in the one above it. The quiet you notice is not the lack of activity, it is the balance of forces over long times. If matter were truly still, gravity would gather it and start the motion again. In physics, rest is temporary. Motion is the rule. Even our direction has a name. The sun moves through the galaxy toward a point in Hercules. The Milky Way as a whole moves toward the Great Attractor, and beyond that toward the Shapley supercluster, the richest mass concentration in our region. The deeper we look, the more layers of motion we find, each a part of a larger pattern. There is no final outside that stands still, only flows inside flows. This sounds abstract until you follow the same rules at home. The gravity that guides galaxy paths also holds you to the ground and keeps the moon in orbit. The same math that describes falling apples describes star clusters and spiral arms. Because those rules are steady, we can measure and predict. We can model millions of years of motion and match those models to what we observe. Computer simulations show this clearly. Start with a nearly uniform gas of dark matter and ordinary matter in the early universe. Let gravity act. Dense knots grow. Gas cools and sinks into them. Galaxies form. They gather into clusters and link along filaments. The picture evolves, but the web remains, not alive in the biological sense, but changing in a way that looks like growth, because gravity always works the same way over time. The idea of rest fades under this view. Earth rotates once per day, orbits once per year, and moves through the galaxy at hundreds of kilometers per second. The moon circles Earth. Every atom in you follows each layer of motion at once. You feel none of it because nearby things share the same paths. The shared frame makes motion feel like stillness. Motion also supports habitability. A stable orbit keeps Earth's temperatures in range for liquid water. A stable lane in the galaxy keeps our region calm enough for life to persist. Expansion on the largest scales keeps far regions from collapsing together. Balance comes from movement, not from stopping. There is a deeper connection too. The atoms in your body were formed in stars that orbited other lanes of the Milky Way. Those stars ended, returned their elements to space, and that material joined the cloud that became the Sun and Earth. The particles in you still orbit, still move, still take part in the same circulation. Cosmic motion is not apart from us. It is the setting of our existence. As space moves through time, the pattern changes. Galaxies merge, clusters separate, the web stretches. Local systems like ours keep their internal order while the larger map evolves. Think of it as eddies in a river. Small swirls remain coherent even as the river flows. Our sense of calm on Earth is one of those eddies. If you could watch the whole history in one glance, you'd see matter collect, stars light up, galaxies assemble, clusters grow, and shock waves spread. You would see the quiet drift we feel now as part of a coordinated motion made of many simple rules operating together. From inside, it looks still. From outside, everything is moving. That wider context brings us back to our near neighborhood. The Milky Way is part of the local group, a family of more than 50 galaxies held together by gravity. Two large spirals, our galaxy and Andromeda, dominate. Both have sweeping arms, a central bulge, and hundreds of billions of stars. Andromeda is near enough to see as a faint blur in a dark sky. That blur contains perhaps 1 trillion stars. Its light began the trip long before humans existed and crossed intergalactic space to reach us. Around both big spirals, smaller galaxies orbit like distant moons. The Milky Way counts more than 50 known satellites. The brightest are the large and small Magellanic Clouds, visible from the southern hemisphere as 2 soft patches. They are irregular, much smaller than our galaxy, and follow stretched orbits. Streams of gas connect them to us, evidence that gravity is already reshaping them. Other satellites, such as the Sagittarius Dwarf and the Canis Major Dwarf, lie so close that the Milky Way is pulling them apart now. Their stars are being added to our halo as long, thin streams. Some of the stars we see belong to those remnants. This is how big galaxies grow. They do not build every star in place. They add smaller systems over time. The spiral disk and the diffuse halo include debris from many past meals. Andromeda does the same with its own companions. The pull between the two giants is stronger than the general expansion at this distance, so they move toward each other rather than apart. In about 4 billion years, they will meet, pass through one another, and merge. Almost no star will strike another. Space is too wide, but their gravity will reorder orbits and compress clouds, lighting fresh waves of star birth. The end result will likely be an elliptical galaxy rounder, smoother and larger. If the sun still shines then, it will be older and dimmer, circling quietly inside a new structure. The local group spans roughly 10 million light years. Most of its members are small dwarfs, some with only hundreds of thousands of stars. They are fragile and easy to disturb, but they matter. Their gas and stars feed larger galaxies and keep the cycle going. Each member's path reflects the combined pull of all the others. The group's center of mass sits in the space between the Milky Way and Andromeda. The two big spirals orbit that shared center, slowly spiraling closer. The dwarfs trace loops around them. Despite all this motion, the arrangement is stable on long timescales. Some tiny members will be absorbed, some will drift out. The main relation will last until the merger rewrites it. Beyond the group lies the local sheet, a broader, flatter collection of nearby groups. That sheet sits inside the Virgo supercluster, which fills a region more than 100 million light-years across. And even that is just one strand in a larger filament of the cosmic web. The local group is a knot in that strand. Knowing this places our galaxy in context, not an island, but a junction in a network. We can trace this story in observations. Star streams arc across the halo fossils of past mergers. Clouds of hydrogen bridge one galaxy to another. Satellite orbits show patterns that point to earlier passes and tides. The Milky Way and Andromeda likely formed from the same larger seed of matter. As they grew, they gathered the material around them and captured satellites. Their present motion records that shared origin. In the night sky, almost every bright point belongs to the Milky Way. A few pale patches do not. Andromeda, the Triangulum galaxy near it, the Magellanic Clouds in the south. These are our visible neighbors in the local group, a tiny sample of the billions of galaxies beyond. Inside the group, gravity wins, so members stay bound despite expansion. Outside, expansion dominates, and groups drift apart. The universe's pattern is a balance. Islands held together, oceans widening. All of this repeats across scales. The local group is like a solar system of galaxies. The Virgo supercluster is like a larger version again. The same laws apply. Gravity binds, orbits form, systems merge. If you could watch from far away, you would see two main spirals, our Milky Way and Andromeda approaching, surrounded by small companions. Some dwarfs would look stretched, others compact. The whole set would drift as one, slow and quiet. In that scene, our sun would blend into a faint arm. Earth would be beyond tiny, yet everything we know would still be there, part of the same network. This neighborhood points us outward to the far limit of sight. There is a horizon to what we can see, not because something blocks the view, but because light needs time to travel, and the universe has a finite age. We call the limit the observable universe. Beyond it, space continues. We just cannot receive information from those regions yet, and in many cases, we never will. The best measurements put the age of the universe at about 13.8 billion years. You might think that would make the observable radius 13.8 billion light-years, but space expanded while the light was on its way. The farthest regions that can send us light now are about 46 billion light-years away in every direction. That makes the observable universe a sphere roughly 92 billion light-years across. It is immense, but still only a portion of the whole. When you look at the night sky, every photon that reaches your eyes has traveled across that history, through distance, through expansion, step by step to get here. When we change scale, meaning changes with it, a grain of sand looks simple from far away. Under a microscope, it shows edges and crystals. The same is true for life. An ant trail becomes a traffic system. A leaf becomes plumbing. A drop of blood is a city of cells. Scale doesn't erase value. It sets the frame in which value can be seen. Our tools stretch that frame. A small telescope turns a blur into a cluster. A larger one separates the cluster into stars. Radio dishes see through dust and find the cold clouds where new stars will form. Infrared detectors catch light stretched by distance and time. No single tool gives the whole, but together they place the small inside the large with more care. That care shows in method. Parallax uses Earth's orbit as a ruler for nearby stars. Standard candles use known brightness to reach farther. Redshift uses the stretch of light to measure the larger scales. In the lab, atomic clocks count electron ticks. In orbit, GPS needs relativity, so your phone knows where you stand. The same physics ties a footstep to a galaxy's drift. The bridge runs both ways. Small systems carry deep time. Coral rings record seasons. Ice cores trap air from ancient winters. Tree rings mark drought and flood. Inside minerals, radioactive decay keeps time for rock. These clocks place human years inside planetary ages, and planetary ages inside the life of the Sunday. Talking about the galaxy's orbit is not separate from us. It is the slow backdrop in which every local record was written. Smallness also supports stability. A planet like Earth can hold an atmosphere. Gravity is strong enough to keep air, not so strong that heat cannot move. Oceans move energy from equator to pole. A thin ozone layer filters harmful ultraviolet light, but lets enough through to drive chemistry. Details of thickness and tilt, salt and pressure, day length and season matter. Life fits inside those details. Scale sets the range where balance is possible. At human size, we meet the same pattern as in space, mostly emptiness, with structure threaded through it. An atom is mostly space. A room is mostly air. A city is mostly roots. A galaxy is mostly vacuum. In each case, the empty part allows motion. Motion allows contact. Contact allows change. Where nothing can move, nothing can organize. Where there is some room, systems form and last. Smallness lets us think. A brain is not large, yet it has billions of neurons, each with many connections. Out of those links come memory and imagination. With them, we draw models of worlds we cannot visit and check them against what the sky and ground report back. Model, check, revise. That loop turns signals into understanding. It is tiny beside a galaxy, yet it tells us how galaxies behave. Return to scale, and the logic echoes. A planet is a stable pattern of heat and mass. A star is a stable pattern of pressure and fusion. A spiral arm is a stable pattern of density moving through disk material. A filament is a stable pattern of gravity, shaping the paths of galaxies. The details change with size. The rules keep their form. It helps to write our address in nested lines. A person on Earth, Earth around the Sun in the Orion Cygnus arm, the arm in the Milky Way disk, the disk in the local group, the group in the local sheet, the sheet near the Virgo cluster, the cluster along a filament, the filament inside the observable universe. Each line names a larger container. None cancels the smaller one. Your address holds all at once. Meaning moves with that nest. A sunrise is weather and orbit. An eclipse is geometry and gravity. A comet is chemistry and history. A meteor shower is Earth crossing a dusty trail left by a small body warmed by the Sunday. That trail was set by heat, spin, and gravity long ago. At each link, Small parts add up to a scene we can watch with our eyes. Scale is practical in quiet ways. The tides that move water also move rock over long times. The sun's 11-year magnetic cycle nudges radio noise. The moon's pull shifts timing for some animals. Slow wobbles in Earth's axis move climate bands over thousands of years. Tiny timing corrections in satellite clocks keep maps true. The laws that shape galaxies also run every device that relies on fields and time. The sun's local light and the universe's background light are not different in kind. Both are photons born of changes in matter and energy. A green leaf's color is a small band of the sun's spectrum. A microwave receiver's hiss is light stretched by expansion. We are adapted to one band, but instruments make the others real. The more bands we include, the more complete the picture becomes. Using the right unit for the right job is a form of clarity. Kilometers for roads, astronomical units for orbits, light years for stars, millions of light years for galaxies. Switching units admits that no single measure fits all scales. That switch steadies thought rather than blurring it. Smallness grants resolution. A coarse photo misses detail. Fine pixels show texture. Life is like that. The more fine-grained the structure, the more ways it can respond. A simple molecule can do few things. A cell can do many. A simple environment yields simple forms. A varied one yields variety. The Milky Way hosts many environments. Dense clusters, quiet lanes, turbulent birth clouds, bare regions. Outcomes differ with setting. Our lane is quiet, which fits the long times life needed here. When we call the stars uncountable, it is not because numbers fail, but because counting is not the best lens. Better is to ask how stars are arranged, how they move, and how they exchange matter with the space between. That turns a tally into a map. It is the same move that turns a list of cells into a body, or a list of words into a sentence. Pattern matters more than raw totals once scale grows past sight. Horizon also scales down. Every tool has a limit to what it can resolve. A microscope's optics set one, a telescope's aperture and wavelength set another, a detector's noise sets a third. Within those limits, detail appears. Beyond them, signal blends into background. Improve the tool, and the horizon moves. The observable universe's boundary works the same way, but its limit comes from time and expansion, not hardware. Knowing where a horizon sits is part of knowing what a result means. You can feel this in simple stargazing. On a dark night, the Milky Way looks like a soft band. With binoculars, the band breaks into many stars and dark lanes. Through a small telescope, open clusters show patterns with names and ages. Through a larger one, faint galaxies appear that never show to the eye. Each step adds features without denying the others. The sky is not different. Our access changes. Small clues guide large inferences. A compass needle aligns with Earth's field. A ring of tree growth tilts with the season. A fossil line echoes an old sea. In space, pulsars tick like clocks, letting us trace motion across vast spans. A slight delay in a radio signal from a probe can reveal a planet's field or the density of a ring. Tiny shifts point outward to big causes. The large writes into the small as well. A supernova seeds a region with heavy elements. Later, that region forms planets with iron cores and rocky crusts. A passing dwarf galaxy can raise a wave in the Milky Way's disk. That wave changes star orbits by a few kilometers per second and leaves ripples we can still measure. Large does not float free. It leaves marks. Language has to work harder at these edges. Words like near, far, long, short, hot, and cold are tuned to human life. Anchors help. Near is a light second for Earth-Moon, a light minute for Sun, Earth, a light year for the solar neighborhood. Long is 1 billion years for continents, a few million for a bright young star. With anchors, pictures stop slipping. The feeling of smallness shifts once anchors are in place. You can be tiny compared with a galaxy and still be well-sized for understanding it. The galaxy does not care about sizes. It runs on laws. We can learn those laws because we live in a niche where stable records can form and be passed on. Our place is small, but it is also clear. It is also shared. If beings live in another arm of the Milky Way, their addresses would stack like ours, and their horizons would center on them as ours centers on us. They would be small at their scale too, and would use tools to extend their reach. They would map their group, name neighbors, and watch their sky shift slowly. The pattern of making sense would repeat even if the details did not. This brings us back to the simple question that started our drift. How small are we inside the Milky Way? Small enough that our star is one among hundreds of billions, and our system vanishes in a view of the whole. Large enough, in the right ways, to see, to measure, and to place our story inside the larger one with some precision. Our size allows focus. The galaxy's size allows context. Between them is the space where understanding lives. Stand outside on a clear night and let your eyes adjust. You are scaled to ground and breath. Above you lies a band scaled to orbits and arms. The light that reaches you is small in energy, but vast in time. It enters your eye, triggers a tiny change in a cell, and becomes a signal. From there, it becomes position, shape, and memory. Something that began in a star ends as a pattern of thought. That path runs across scales without breaking. From here, it is natural to ask what other paths cross these scales. Paths of matter from clouds to planets, of energy from stars to chemistry, of motion from local swirls to galactic tides, and how each path leaves marks we can read next. Think of scale as a set of doors that all open into the same house. One door leads to breath and heartbeat, another to clouds and shorelines, another to stars, another to the dim glow between them. Walk through any one of them with care, and you end up in the same place, a pattern that holds together without rushing, a logic that repeats in different keys. Small is the note, large is the chord. Neither plays without the other. When we say the galaxy surrounds us, we don't mean a picture hanging above our heads. We mean the air we draw, the light we see by, the salt in our blood, the carbon that stitches thought together. We mean a quiet continuity from cold dust to green leaf to word on a tongue. Awareness doesn't stand outside to take measurements. It rises from the very materials being measured. The observer is another arrangement of the observed. It helps to trade counting for listening. Numbers are good at stacking facts. Listening catches the thread that runs through them. Listen to how near and far are always the same conversation. A photon leaving a star and a signal crossing a neuron follow the same rules. A tide against a quay and a planet in its lane obey the same pull. The difference is tempo, not text. The universe is a score written for many instruments, each keeping time in its own register, all following the same meter. If you let go of totals, you begin to see relations. A star is relation between gravity and fire. A planet is relation between light and shadow. A forest is relation between soil and sky. A city is relation between roots and need. A mind is relation between memory and surprise. The Milky Way is relation braided from countless such relations, a long weave that holds shape because its threads keep moving. Movement is the quiet background of everything, not noise, not chaos, balance in motion. Stones settle, clouds shear, roots seek, rivers learn the slope, earth turns, the sun drifts, the arm of the galaxy curls, the great lattice beyond stretches and sighs. None of it asks permission, none of it hurries. You are carried by it as surely as a leaf is carried by a stream, yet you can look down through the water and make out the stones. That is the peculiar gift of being small. You move with the current and can still make sense of it. Meaning gathers where movement slows enough to leave a trace, a ring in a trunk, a ripple frozen in sandstone, a ritual remembered from season to season, a formula scratched on paper that helps a lens find faint light. Traces become maps, maps become stories, stories become ways of walking. In that way, knowledge is not a pile, but a path, steps set by many feet, curving through the same country, returning to certain overlooks because the view there helps you go on. If you've ever stood under a dark sky and felt both at home and a little unmoored, that's the body recognizing its scale. The feeling doesn't accuse you of being less, it invites you to belong. Belonging here is not ownership, but fit. You fit the window of conditions where water runs, where chemistry keeps its promises, where memory can persist long enough to pass a pattern forward. This fit is not an accident you earned. It's the shape of your participation. Seen this way, humility is not a posture, it's geometry. It's the recognition that every contour of your life is drawn by larger curves, the tilt that brings seasons, the cycles that cue migrations and moods, the slow drift of the heavens that nicks calendars and myth. Humility doesn't flatten you, it places you. It says, you are not the center. You are inside the centerless whole, threaded, supported, implicated, needed, precisely as you are. The mind likes oppositions near and far, tiny and immense, self and world. But the more you look, the more those oppositions blur into gradients. A cloud is both local and galactic. Moisture lifted by sunlight that started as nuclear fire, shade shaped by mountain and wind, whose patterns recall the eddies of stars in a spiral. A thought is both private and universal, an intimate spark following rules older than dust. The miracle is not that the same law holds everywhere. The miracle is that such sameness leaves so much room for variety. Variety is how the universe speaks in paragraphs rather than bullet points. Snowflakes are many, but not the same. Leaves on a single tree share a plan, but improvise toward light. Voices in a choir hold a pitch, but weave their own accents. Stars follow shared physics yet live wildly different lives, and from their endings come the ingredients for oceans and lungs, and the quiet electricity that lets a sentence finish in a new way. The Milky Way is not a copy shop. It is a workshop, and time is its artisan. What then do we do with the ache that shows up when we try to picture all this? Not swat it away, let it do its job. That ache is how the scale of things stretches the frame of a day without tearing it. It's the mind's way of making more room. Sit with it. and you may notice that it carries ease inside it. Ease that comes from realizing that you don't have to hold the whole, only be held by it. That you don't have to see every star to stand honestly in their light. From there, gratitude arrives, without ceremony, for warmth on skin, for shade on a hot walk, for a sound that rings true, for the way a night breeze bends a branch and the stars behind it don't flicker, for a sentence that steadies, a hand on a shoulder that steadies more. Gratitude is not a denial of measure. It is measure tuned to sufficiency. It says, this much is enough to go on. This much is enough to care for. This much is enough to learn from again tomorrow. And caring scales. Care for a cup becomes care for a river. Care for a patch of soil becomes care for a climate. Care for a child becomes care for a future none of us will see, but all of us can influence. There is nothing small about such care. It is the practice of fitting our actions to the size of their consequences, which is to say, fitting our lives to the truth that everything we do takes part in currents wider than intention. If words must be simple, let them be these. You are not apart from the galaxy. You are a form it takes for a while. Your breath trades with leaves grown by a star. Your steps borrow firmness from rock pressed by old seas and old fires. Your thoughts kindle because the elements of extinct suns learned how to hold and release energy in just the right ways. The fact that you can notice any of this is not an accident added on later. It is a feature built into the weave. So you can set down the tape measure and take up attention. You can let night be night without counting. You can trace a few constellations not to master the sky but to remember the path home in the dark. You can read the slow news of dawn across a window frame and feel how gently the world turns. You can share that feeling with someone else and watch it steady both of you. These are not small acts. They are acts that sit at the correct scale for a creature that is both specific and continuous with everything. If tomorrow brings cloud, the galaxy is still there. The work of its many parts goes on. If tomorrow brings worry, the currents remain. The task is still to place one good thing in the flow and trust that the flow will carry it beyond your sight. If tomorrow brings joy, notice how easily joy echoes the structure of the world. Light distributed, warmth shared, motion without friction. All of this is practice in staying aligned with the slow turning we belong to. In the end, not the end of things, only the end of a thought. The image to keep is modest. A person at a window, the hum of a quiet room, the pale idea of a river of stars beyond rooflines and cloud. A breath in, a breath out. The sense, as steady as a heartbeat, that nothing in this scene is cut off from anything else. That the galaxy is not above the ceiling of the sky, but threaded through the grain of the table, the salt on the tongue, the memory that rises uncalled and kind. That noticing is participation, and participation is enough. Let that be the measure you carry, not the span from here to the rim of sight, not the count of lights in the dark, but the felt truth that scale is a language for belonging, and you are fluent enough. The Milky Way turns. You keep time. The stars send their quiet story. You answer with a smaller one that rhymes. Between those stories, the distance is not far. It fits in a breath, and then another still.